Let's take a closer look now at some common types of exponential models. When we first explored exponential growth, we were looking at the equation y equals ab to the power of x. Well, in this case, we have a slightly different function notation, but all the key features are still there. A is our initial amount still. There's no change in that. But instead of using b to represent our base, now we kind of think of it in terms of r as the rate. Same exact concept, but how we find the rate is we actually are going to be either adding or subtracting from 1 a percentage of whatever the change is. T is now the independent variable, representing the number of time periods that are elapsed. Now, as far as our rate goes, it's really important that if our rate is greater than 1, we have an exponential growth in our equation. But if it's between 0 and 1, we have what's called an exponential decline or a decay. Popular functions are population growth and decline, as well as compounding interest. Now, population growth and decline, we'll see growth or decline. Interest is typically going to be a growth. Otherwise, it's not really interest. So we have an initial value here of 75. And then here we have a 4% growth. And the way we find that is we take what our R value is, which is 1.04, and it has to equal either 1 plus or minus some percentage. Well, in order to get 1, we have to add, the percentage has to be 0.04 in order for it to add up to 1.04. And so then we can find that it's a 4% chance. So looking at a couple models, the function p of t models population of a rural village t years after 1996. Well, if we want to know the village's population in 1996, that's when time equals 0. That's the starting value. And so the starting value is 680. Well, how do we know that 680 is the initial value? Well, let's take some time and actually evaluate the function for p of 0. If we take anything and we raise it to the 0 power, it always equals 1. And so once we do that, we see that p of 0 equals 680 times 1, which is just the 680. So we know that the initial population was the A value, 680 people. Now, by what percentage is the village's population growing or declining? Well, first we need to figure out, is it a growth or a decline? Well, we look at the R value. And since R is less than 1, we know it's going to be a decline. We just need to figure out how much less than 1 it is. So we take 1 and we subtract the R value. And that gives us 0.06. If we rewrite that in decimal notation by multiplying by 100, we get a 6% decline. Using the same idea, we can go ahead and actually write our own function that models the reservation population of deer. So we're looking for p of t equals a r to the t. Well, a is our initial value, and since it started with 170 deer, that's our a value. Now, r is going to be found by adding or subtracting 1 by the percent. Well, here's our percent, and we know it's an increase. So that means we're going to add 30%. 30% as a decimal is 0.3. So we're going to be taking 1 and adding 0.3, and then we keep our exponent of t. So simplified, our function is 170 1.3 to the power of t. Here we have another function that models population after 1996. To the nearest whole number, what was the net increase? Well, in order to find the net increase, we have to know how many people in 1996 and how many people in 2002. Well, again, this is times 0. So p of 0 is always going to be equal to the initial value, 227. 2002 is time equals 6. It is 6 years after 1996. So we want to solve for P of 6. So when we evaluate, we get approximately 271 rounded to the nearest whole number. So to find the net increase, we just find the difference between the two. The net increase is 44 people. Here we can write a compound interest. UG put 500 into savings. That's our initial amount. So the principal over time equals $500 times a 1% interest. So it would be 1 plus 0.01. That's 1% in decimal notation to the power of t. So we can simplify. And he wants to know how much money after 5 years. So we will evaluate P of 5. Which, when rounded to 2 decimal places because it's monetary, $525.51.